opening remarks. I'll just observe that the MIT Energy Initiative, which started late 2006, early 2007, from the get-go, we had a focus on engaging with industry as we look to understand how we meet the grand energy challenges in front of us. And to do that, we instead of trying to set up our own industrial relations group, we decided to partner with ILP. So Carl and his team, Corey, have been an instrumental part of MITEI since we got going, and we continue to enjoy that great relationship. So I'm going to give a brief, given the time and given the kind of content I want to get across, a brief overview of MITEI, the MIT Energy Initiative, and then within that talk just a little bit about the Future Energy Systems Center, which is a new venture that we've started. Just last month we officially launched it, although it was announced when the MIT Plan for Climate Action came out in May. The grand energy challenge that we're looking to address at MITEI, and what brought us together as a faculty, is a twofold one. And the first part of it is that we project, and groups around the world project, a substantial growth in energy demand by end of century, something like a doubling. And that's driven by population growth, increasing standards of living, particularly in emerging market developing economy countries, right, where the rapid growth is going to occur. So how do we supply energy those people need in order to improve their standard of living? At the same time, we obviously have to mitigate climate change. We have to deal with the elephant in the room, which is how do we increase energy access and at the same time remove emissions from the energy system and the economy as a whole. So that's the two sides of the challenge that we're looking at the Energy Initiative. We started, as I said, back in roughly the beginning of 2007 as an institute-wide initiative. This was the concept of Susan Hockfield, who was president of MIT at the time, as a way to bring faculty from across campus together in order to get the kinds of disciplines we need, talking together to address that dual challenge. And we've worked hard to do that and have engaged to date about 500 faculty at MIT. Those faculty are not all the same at one time. There's some who have retired now who were in the early group there, but we're continually bringing in new faculty as we seek to get new ideas and new disciplinary strengths to the table in addressing the energy challenge. Carl cited, I think, $750 million that we've brought in since we launched. Happy to say that number continues to rise. We're now a little past 860 and counting. And I think one of the things I'm most proud of is that we've engaged all 5 of MIT schools plus college and engaged those in depth. And so I think that's been an important part of our success. We of course, look broadly at research. This is a research university. We engage in education. We have developed an energy minor at MIT. We have new ventures in online education. We're about completed with 4 subjects for a online MicroMasters. We have about 38,000 students taking energy-related courses. Interestingly called the Future Energy Systems program. We have, as Carl mentioned, startups. We've stimulated a lot of new ideas, which have in part helped MIT to spin out some 100 startups in energy since we launched back in 2007. So that's a few of the things we're doing. We of course, are very interested in the energy sector, and that includes the power sector, how we generate power, the industrial sector, how we use energy for making goods and services. The transportation sector, which includes light-duty vehicles, but also air freight transportation, and then finally buildings, commercial and residential buildings, or the built environment. As this diagram shows, those sectors are not isolated. You don't look at them one at a time. You look at opportunities in each of those sectors, and those opportunities are strongly related to how those sectors interact with one another, right? So how we get overlap between the power sector and transportation, for example, with increasing electrification of the transportation or the light-duty fleet. And there's similar overlaps with the other sectors. I also point out two themes in the upper left, lower right, which don't fit neatly within one of those sectors, but impact our ability to deliver on a need for net zero emission by 2050. And those are carbon management in the upper left, and in the bottom right, low carbon fuels and storage. And so those are areas that we're deeply interested in at MIT. I mentioned earlier that we have brought in about $860 million in funding. The bulk of that goes to research. We have a very vibrant research portfolio at the Energy Initiative. An interesting part of that has been a seed fund program that we launched when we first started, in which we award an annual round of seed fund projects, about $150,000, just to get an idea started. So any faculty member or principal investigator at MIT can submit a proposal with a new idea in energy, and that's about all there is to the restriction on the topic. And we're trying to find out who out there has new ideas, who's got new disciplinary strengths that could be useful to other faculty and to us in addressing energy challenges, and to stimulate new lines of research. We've done, in this most recent year, another 7 of these projects for $1.2 million, and our sponsors have picked up another 8 of those project ideas that couldn't be funded out of the core consortium funding for those startup projects. But all in all, we've gotten, we're closing in on 200 seed fund projects in the upper 20 million category, and that has resulted in interesting startups, interesting new government-sponsored projects, interesting new industrially sponsored projects, and so on. So I'm not going to spend very much time on the research portfolio, but I do want to say a few things about what we do in research, just to keep you, make sure you're aware of that as a very strong underpinning of the Energy Initiative. This is an example at work we're doing to zero in on how can we capture carbon more cheaply. We know how to do carbon capture at scale, but we do not know how to do it cheaply enough so that it will scale up. There are promising signs in the new infrastructure bill that was just signed Monday. There is substantial funding for carbon capture and management. And we hope that will, coupled with new ideas, help stimulate adoption and scale up of some of these technologies, which will be badly needed in the 2030s and 40s if we want to get to net zero by 2050. This is an example from Professor Alan Hatton's lab in chemical engineering, looking at a novel electroswing adsorption technology. So he uses a structure that looks like a battery in a way. It's very modular, which is an advantage for scaling, in which you pass CO2-laden gas between the plates, and depending on the voltage you apply, you can either adsorb or desorb CO2 from the surfaces of these electrodes. And with one train that's adsorbing, one train that's desorbing, then you can have a continuous process for capturing CO2. One interesting aspect of this is that this seems to work equally well for very concentrated systems, something you might get out of a flue gas, or for dilute systems, think direct air capture technology. So that looks quite interesting. Another faculty member, Asa Henry, in mechanical engineering is looking at ways to take methane and convert it to hydrogen with zero carbon emissions. And he does that with a really clever process for pyrolysis. Pyrolysis, of course, is not new, but this way of doing it is. One of the challenges in the pyrolysis reaction is that you have to go to very high temperatures if you want to get complete conversion of the methane to hydrogen and carbon. And the way that he does this is to bubble the methane up through a molten tin bath, which is at 1400 C, at which point you get a complete conversion. And in doing that, he gets the hydrogen gas, which then bubbles out of the system, easy to capture. And the carbon is in the form of carbon black, which floats on the surface of this tin bath and can be skimmed off. So really innovative idea, which he's pursuing. The last example I'll give in research is one I'm sure you've heard about if you're on campus here, and that is the work in fusion that MIT is doing. And this is a picture of the demonstration back in early September the 5th, in which the group from Commonwealth Fusion System, they're one of MITEI's members, and the Plasma Science and Fusion Center at MIT, which has a lot of decades and decades of expertise in the field, demonstrated a high temperature superconducting magnet so you could achieve higher field strength than has ever been done before for a magnet in this area. In this case, they demonstrated over 20 Tesla, which should enable a decrease in volume of the reactor required for a given amount of power of about a factor 16. So very substantial. They are now in the process of building what they call a spark reactor. That's the first demonstration of an at-scale net production of energy in a fusion system. So we're excited about that. I mentioned earlier that, or maybe Carl mentioned, some of the new actions on campus. There's one of these is the MIT Plan for Climate Action for the decade, or the Climate Action Plan 2.0. That was announced in May. It has lots of components to it, but two major aspects. One is do what you could do now with what we have available, and secondly is develop those technologies, policies, institutions that we don't have that allow us to get to net zero by 2050. MIT has a very interesting array of activities. The Energy Initiative plays in the innovation area in this, in education, in policy areas. I'm going to tell you about one piece of the innovation area this morning, and that's the Future Energy Systems Center. The idea in the Future Energy Systems Center is to look at those parts of the energy sector that I showed and look deeply at how those interact with one another to understand how component technologies that we work on today, how businesses that you have in specific areas of energy, whether it's in production, conversion, transmission, distribution, end use, how those fit together in a changing energy system. So as new technologies come available, as new business models come available, how does that integrate into this system and to the economy more generally? So we want to provide important insights into that to our members, and we currently have about 25 members of that center, and we're looking to grow that to about 40 at steady state. As I said, we launched this just last month, just a little over 4 weeks ago. In the Future Energy System Center, there's an initial focus on 6 themes. There's obviously lots of things you could do, and we felt important to try to focus down. We are looking at these 6 areas as our initial target. There's the electric power sector, the industrial sector, transportation, and the built environment, and then these 2 cross-cutting areas I mentioned on a previous slide, carbon management and low carbon fuels and energy storage. One of the I think great strengths of this center is that it builds on about 8 years of a set of low carbon energy centers that we hosted at MITEI through the first climate action plan at MIT. And in that process, we built up a lot of expertise in life cycle analysis, in techno-economic analysis of these technologies, and ways to understand systems behavior. And I'm going to tell you some stories of how we do these cross-sector analyses using 3 of the models that we have available in this center. The first of those comes from one of our core partners at MIT in this center, and that's the Joint Program on the Science and Policy of Global Change. Sergei Paltsev, who's the deputy director of that program, is a senior research scientist at the Energy Initiative. And they have developed a macroeconomic global multi-region, multi-scale model called EPA. It's the MIT Economic Projection and Policy Analysis Model. It allows us to look at the world at large, broken down rather coarsely into 18 major regions. You can, in some cases, they have subdivisions into much finer scale. But they can look at policy impacts on GDP growth, on different parts of the economic sector, on trade between different regions in the world. Lots of very important things that they can pull out of their analysis. But if you're interested in understanding the detailed emissions and how you build out an energy system in a particular region, you need more detail. And for that, we have developed a model called SESAME. It's the Sustainable Energy System Modeling Analysis Environment. And it allows us to look at essentially any energy pathway, going from an energy source to an end use, and develop rapid analysis of the life cycle impacts, so CO2 emissions and other emissions, and the techno-economics. What does it cost? You can do something as simple as looking left to right in this image. You're not really supposed to be able to read all of this. The idea is to give you the sense that there's a lot of options here. But you can pick out of the first column some energy source. It could be solar. And there you could pick some particular solar manufacturer's PV module. Then you move from left to right on how you move that energy source to some processing step. If we were doing oil, in this case, the processing would be a refinery, say. You move that on to some next step. And there, in this case, there's an optional step, CCUS, that you could put in. In some processes, you might do that, and some you might not. So for example, if we were doing solar to electricity, we wouldn't have a CCUS step. Then you move to a stage where you move that product, say gasoline or electricity, to the end user. So for electricity, go through transmission and distribution systems to the end user. And each of those has a lot of detail, including the emissions and the techno-economics, that you can put together to understand system impacts. And then the third model is a capacity expansion model. It's a model that allows us to look at, given a suite of technologies, and our projections for those technologies out into the future. That is, their technical specifications and their costs, say out in 2050, what system would you build for supplying some energy service, whether that's electricity or some liquid fuel or hydrogen? That's what this Gen X model is for. And it can go from the energy production part of the system, so large generators to distributed generators, down to household nodal levels. So it can go at a very fine scale. So let me very briefly give you some windows in what you can do here. An example of using EPA together with Sesame has been looking at transportation options. In particular, we focused in a recent Mobility of the Future study on light-duty vehicles. So imagine in this picture going left to right from some energy source, could be oil for gasoline spark ignition engines, or solar or wind to an end user to charge a battery electric vehicle. So a suite of options there for powertrains and vehicles. And we get a fleet model, initial set of conditions from EPA that we can put into the Sesame model. With that, then, we can generate emissions life cycle analyses for different light-duty vehicle options. This looks at comparisons of the emissions per mile driven for ICEs, internal combustion engines, for hybrid vehicles, for plug-in hybrids, for battery electric, and for hydrogen fuel cell vehicles. I won't go into too much depth here, but I'll say you'll note there's 3 different colors in those bars, and those represent the emissions associated with making the vehicle, with making the fuel, and with using the fuel. And all of them have a component from making the vehicle, from making the fuel, and from, not all of them though, have a contribution from using the fuel, right? So that shows how those compare. With a model like Sesame, you can dive much more deeply into how that vehicle fleet interacts with the power sector, for example. The colorings on the map show how the grid emissions in different parts of the U.S. impacts the relative emissions of a battery electric vehicle to a hybrid electric vehicle. So the green ones, like Washington, which uses hydroelectric as a dominant electricity source, is very green compared to a hybrid vehicle, whereas states that use more coal in their energy systems, electricity systems, are gray, and they have worse emissions for BEVs relative to hybrid electric vehicles. I zero in here on California and New York to see if you want to get the biggest emissions reduction from a battery electric vehicle, when would you charge it? And it depends on what the energy system looks like in your area. If I'm in California, the grid is cleanest in the daytime when the solar resource is dominant. And so I'd be better doing daytime charging. In New York, I'm better off charging at night because peak demand is gone, and I've been making up that peak demand with natural gas. Nuclear, which is base load in New York, has a larger role in the energy system at that time of day. And so it's better off in New York to charge your car at nighttime. I'm speeding through here because I'm running out of time, but I wanted to just show briefly an example looking at intersections between the industrial sector and power. And the example we've used is to look at replacing natural gas for powering industry with hydrogen that's produced electrolytically. We've used Texas as a case study because Texas has very substantial natural gas use for industry. So we've looked at scenarios where we replace none of that natural gas with hydrogen up to 100% of the natural gas with hydrogen, And we're interested in what's the emissions reduction impact from that, and what's the impact on cost. And we look at that in a number of different scenarios. The scenarios are based on policy limits on grams of CO2 that you can emit per kilowatt hour of energy produced. Right? So the bottom set of panels here, the bottom row, is for no limits on emissions, so the current situation by and large. And the top, they've gone down to 1 gram of CO2 per kilowatt hour of energy produced. The one thing I'll focus on here is that in the upper right, there's the system cost of electricity. The rightmost column gives system cost of electricity for all those different emissions limits. And you'll note that the bars at the top of the system cost at each emissions cap is the smallest bar. So you get the cheapest impact, the cheapest system cost of electricity if you do 100% replacement. The reason for that has to do with better asset utilization of the variable renewable resources, wind and solar, plus better asset utilization of the electrolyzers. And you take advantage in this system of being able to store the hydrogen in caverns or surface storage to keep industry going 24/7. Last example, to be really short, is looking at buildings and the power sector and that intersection. This is a look at India, where one of the emerging market developing countries where we expect very large energy demand growth. This looks at the World Energy Outlook projections out to 2050. What I want to call your attention to is the orange piece of that, or gold piece of that. That's the largest demand growth. That's from the building sector. And the reason that grows so much is because of air conditioning load anticipated increases. So that's going to be one of the big drivers for energy demand growth in a country like India, and it's driven by a ever increasing size of a middle class there. You'll also notice in the table on the bottom left that as we get out to 2050, that's going to be a very peaky demand from air conditioning. It's up to 45% contribution for the peak demand and a 30% contribution to the average annual demand. So let me just skip to show this one last slide, which is a look at the impacts of decreasing storage cost in that system. I call your attention to the middle panel here, where if we successfully can drive down costs of storage, particularly long duration storage, as we get out towards 2050, you'll see much lower emissions. And in fact, this is done without policy. You drive new coal out of the system, but existing coal remains an important part of the Indian system without policy. And we can talk a lot more about that offline if you're interested. So let me stop with these observations, is that as we talked about, the energy system is a highly integrated system, and we need to understand what that integration looks like and how those parts play together. They'll play differently in different parts of the world because different parts of the world have different resources. Some places you'll have hydro, good solar, good wind resources. Others, New England, for example, we have good solar, we have good wind and hydro, but not so great solar for use. So how do those systems differ? And also, just as a final remark, say that we in this center, I think, complement other activities within MITEI, the research, systems modeling, and policy analysis. I think it also complements well other things going on in the MIT Climate Action Plan, including the Climate Grand Challenges and the Climate and Sustainability Consortium, which you'll hear about right now. So thank you very much. I appreciate your attention. We're done. I'll take one.
Okay.
Yeah.
Thanks, Bob, so much for the talk.
So it's not a short bill, but there's a huge opportunity for energy research and for industry in this bill. Two examples I mentioned earlier: the funding for carbon management, for carbon capture, and incentivizing that. The second thing I'll mention is hydrogen. There's, I think, about $9.5 billion in the bill for hydrogen. Some of that is aimed at hydrogen hubs, and there's the plan for 4 hydrogen hubs, regional. It's everybody's guess where those will be, but I think some good guesses are Houston. Second good guess would probably be the LA area. Third and fourth, I think we could debate more, but I think there's a great play in those hubs, because the idea is to bring different industries together to look at, if you have a concentrated availability of a resource like hydrogen, how can those different industries work together in both supplying and also the end-use applications of that hydrogen. That is just the tip of the iceberg. We're actually spending a lot of time right now digging through the bill, but anyway, there's a lot there for energy. Thank you very much.
We'd love to actually take a few more questions from you, if that's okay. We've been told that there's a couple more minutes, so if you would please continue with questions, we'd love it. Thanks.
Can do a few more. I've got other conference to do.
Okay, that's right.
Sorry.
Okay, well then maybe
Let me
we
see
can
how
take,
we're doing.
This
Yeah,
question.
just
Thanks so much.
if you could make it big again on here. Say what understanding of the cascading effects of climate change do you have to be confident that catastrophic change is not closer than what the models predict? Should have stopped at the last question. So one of the observations from the last IPCC report is that although we are not on the path yet to net zero emissions, that we have, in what different countries and different companies have done in the last, since the last IPCC report, that we've taken the extreme cases off of the table now. So the bad news there, of course, we took the extreme good case that we get to 1.5 in an easy route, but we've taken off some of the worst case scenarios. So if we continue on a path like now, we're pretty confident we would end up somewhere like 2.6 degrees, which is too hot. But we are very unlikely to get out the 4.5 degree scenario and higher have been taken off the table. And I think that's encouraging, but there's a lot more work to be done. One of the analyses from IEA from just post COP26 is that if the pledges that were made at COP26 were fulfilled, then we would be in an 1.8 degree world, which is not there, but it is getting there. So I think given a knee-jerk tendency maybe to be pessimistic about COP26, I think it's a continued movement forward. It's a very complicated system to try to get all the governments of the world together to do something when you can't require them to do anything. And I think though we are successfully moving in the right direction, you see the progress through the extreme high temperature scenarios being taken off the table, but that's not to say we don't have a lot of work to do. But you're going to be an important part of that, right? And then it's industry. We're getting to the place where industry's got to start scaling this stuff. And I think what we're trying to help with at the Future Energy Systems Center is to understand the economic benefits for doing that, and to understand what the business case is, and to understand what your impact is on reducing emissions from what you do. So thanks very much.